Shall we start now? Bhaskar?
Yes, sir. It is audible, sir.
The PPT is visible?
Visible, sir. Yes, sir.
Okay. It's okay, fine.
Yes, sir. Is it visible fully, sir? No.
Okay, fine. You take that geotag, okay? Hello? Hello?
Yes, sir.
I texted in WhatsApp, just a minute.
Yes.
Just check your WhatsApp, I will send one message. Okay?
Yes, sir. Okay, sir. I'll follow.
Let us start. Okay, welcome to this VSE. Today's topic on OAM for 5G and beyond. This is my lecture outline. First, I'll give an introduction on OAM, then generation and recession of OAM. Then I'll talk about LGBM, which is basically carrying that OAM signal. Then I'll take two different network model, that is system model 1 and system model 2. Then I'll discuss the sum rate of this network. If we look at what is the motivation behind this wave techniques? Why we are looking for such high capacity techniques? Basically, the reason behind that rapid growth of the same reasons, the rapid growth of wireless devices and applications. On the other hand, if you look at that, spectrum is limited, so there is a scarcity in spectrum. So obviously there is a need of new multiplexing techniques which can accommodate more number of users within a way, less bandwidth, and improves the capacity and data rate of the system. If we look at what are the techniques are available, that already that frequency time division time, you all are aware about that. In 4G, that is OFDM, then MIMO and beamforming. These were evolved for high data rate, high capacity transmission purpose. These are from transmitter as well as from the receiver techniques that are already discussed in last class, and I told about the channel, how to control the channel using this. That was another. Today, the question is, can we use another physical dimension of AM wave? Yes, that is possible. That is through OAM. There is a in OAM. What is that? First of all, we should know that what is OAM. OAM is basically orbital angular momentum. Before that, going to this OAM, we should know what is angular momentum electromagnetic waves. We look at here. Their electromagnetic waves can carry angular momentum, which describes rotational properties of the electromagnetic wave. There are two type of basically angular momentums. One is SAM, that is spin angular momentum, where the polarization and all that circular polarization, there is a left circular or a right circular. These are coming in under this spin angular momentum. And another one is the orbital angular momentum, where the spatial phase distributions are used. So angular momentum is associated with the polarization of waves, such as left hand and or right hand circular polarization. In contrast, OM is associated with spatial distribution of the phase of the wave. Now, what is the concept behind this OM? In OM, the phase is changing around this beam axis, and this phase variation is represented by this e to the power j, e to the power j phi l, where l is basically indicates the mode index and phi is the azimuthal angle. That value of L can be can be 0, can be plus minus 1, can be plus minus 2, can be plus minus 3. There is infinite possibilities. But in practice, uh, after 3 or 4, say 5, it is not possible to decode, because that the power of this mode is becomes very low. Okay, so you can say it's not realizable. So when I'm talking about L is equal to 0, L is equal to 0, that means basically with beams like a normal Gaussian beam. When I'm talking about L is equal to 1, that it will take a single one rotation. One rotation. There is a full rotation around the beam axis. That these words may not a little bit confusing. It will be clear when I discussed that beam and all. Uh, just keep in mind that L is equal to 1 is one full rotation around the beam axis, while L is equal to 2 means two rotations. These modes, these modes means whether L is 0, 1, L is equal to 0, 1, minus 1, uh, plus 2, minus 2, all these modes are orthogonal to each other. That is the beauty of this technique. So these modes are mathematically orthogonal. Multiple modes can exist in the same frequency band without interfering each other under ideal conditions. That is the beauty of this technique. Now, why OAM need in wireless communication? Basically, it increases the spatial spectral efficiency without any requirement of extra bandwidth. Okay, means within the existing band, I can accommodate more number of users. For an example, say right now I have a bandwidth B. I can accommodate. Right now I'm accommodating that one user, two users. One is transmitting with mode 0, another is transmitting mode 1. Suddenly, if the number of users increases from 2 to 6, I can allocate different nodes, and they can transmit to the same band. Since they are the modes are orthogonal to each other, they won't interfere each other. So I can accommodate more number of users. So obviously, the bit rate would be high, and bit rate would be high. Okay. Second point, the traditional communication system multiplex signal in time, frequency, or spatial domain. However, OAM introduces new multiplexing dimension. There's a phase structure of electromagnetic. This is a very key word, important word. Phase structure. Okay. OAM is considered as a promising technique for high capacity communication, including 5 beyond 5 to 60 nanometers. Fine. So, how OAM can help in increasing system capacity, since the modes are orthogonal, so more number of users can transmit within the same band. So obviously, easily you can realize the system capacity would increase. Now, already I talked about that. I told you that two type of momentum is there, angular momentum. One is SAM, and another one is the OAM. If you look at here, SAM, that is spin angular momentum. It is just this is a circular polarization. If it is a left hand side, means it is a anti-clockwise, it is moving anti-clockwise. It's a left hand circular polarization. Whereas right hand polarizations, it is going clockwise direction. So this is the basically wave is propagating along this direction, but that wave is rotating along either in anti-clockwise or clockwise. So this is polarization. So SAM is basically talks about the polarization technique. Whereas in case of OAM, that OAM is basically is a helical structure, helical wave. There's a basically, if you look at here, that's it's a phase changes from basically phase structure is different. Now, how I can, if you look at the electromagnetic field, the general one, E is equal to A, that is basically called intensity or amplitude distribution. This is the amplitude of the beam, and e to the power j phi l phi. This is basically represents the phase structure, helical phase structure. So this A that is a function of R and Z. R is the radial. So beam, if you look at the beam, if you look at the beam, it has some radius. If you look at a beam, it has some radius. It has some radius. It propagates some direction, that is a Z. I'll talk later one by one. Z direction, it will propagate some Z direction. So it's a function of R and Z. So that A R Z basically amplitude distribution of the beam. It describes the intensity pattern of the beam, and this it creates the donut shape of the intensity pattern. How the signal is strained, that through the radial positions, that can be described by this R, and how it is that the intensity is changing along the Z direction, both can be described by this ARZ. So basically ARZ is a function how the intensity is varying radial in radial direction as well as its propagation direction Z. This ARZ describes that. Whereas this e to the power j alpha is a helical phase structure. It how the phase changes when the beam is moving. Okay, that is described by E alpha. Already I told you that the value of L may be 0, maybe plus minus 1, maybe plus. So different helical structure of the beam is given. When L is equal to 0, you see this is the structure of the beam. When L is equal to 1, you can see that is only one that rotation is there. When so this is basically anti-clockwise. This is a clockwise. L is equal to -. Similarly, L is equal to 2, L is equal to 3. So there are three forms, circle, 3, 2, when L is equal to 2, that there are two circular moment, that is a rotation is there. When L is equal to, there are three circular rotations are there. You can find. So waves have a helical wave front, and the modes are orthogonal to each other. So the key takeaway from here about this wave beam, they have their helical structure, and it has there is a possibility of multiple wave modes, and each mode, the modes are orthogonal to each other. Now, how we can for better visualization purpose, I have taken this slide. Say one is that spiral phase bond, that donut shape, that is called this type of shape is called donut shape. Okay, and the phase varies from 0 to 2 pi. So L is equal to 0, that already I shown you. L is equal to 1, L is equal to 2, L is equal to 2. So if you look at here, this basically this upper one is basically intensity and lower one is the phase structure. If you look at L is equal to 0, the intensity is at here, the yellow line, here high. As that the value of L increases, the means mode index increases, that you can see that the bright portion slowly that radius basically increasing. Here it is little bit bigger when L is equal to minus or 1. When L is equal to minus 2 or 2, it is much bigger. When L is equal to minus 3 and plus 3, is much bigger than the previous one. So basically L describes how radially it expands, elongated. And the bottom one is the phase structure. Now, how I test that orthogonality in ideally, if the two modes are there, one is L1 mode, other one is a L2 mode. If they are integrated over that phi, then if it is coming 0, that means mode L1 is equal to L2. That is an ideal case scenario. Okay. So how I can do wave multiplexing, since they are already mentioned, these modes are orthogonal to each other. So I can transmit data through this using these modes. So how we can do the multiplex the data for during transmission? Say I have three streams of data. Stream 1 will be transmitted using L1 mode. Stream 2 will be transmitted using L2 mode, and stream 3 will be transmitted using L3 mode. So what would be the total received signal? So I can describe is equal to this one is equal to -1. Say if it is, I say beta I say 0 this is. So I can mention -1 to 1. So the stream 1, stream 2, stream 3 can be transmitted over different modes through the same band, and that this total received signal may be described by this one. Now, how we can generate this OAM wave? There are several techniques are there. The first basic block diagram. Normally, the user that in few reality that data is available, that signal is available in analog nature. You have to digitize the data first. So, what are the first digitization techniques? That you have to sample the data, quantize, then encode. Once you encode the data, then it becomes a data stream 1001. That is a data stream. After getting this data stream, you have to modulate. In that case, you can use QPPS key, you can use QPS key, you can use OAM, depends on your applications or channel condition. After that, we should use that OAM generator used to generate to incorporate this modulated information within this OAM mode and then transmit it. So this OAM generator can be a spiral plate, which is shown here. See this TEM transverse electromagnetic field. It is 0000 means basically a single. Okay, TEM 00. When it is TEM 01, that means it is splitted like this. When I say TEM 02, then it would be splitted into three parts. 1, 2, 3. Now, if I write TEM 1, 2, then it would looks like 0, 0. Sorry, this part. This is out. So anyway, this is not our discussion part. So this is a one transverse electromagnetic wave. When it passes through this spiral plate, this spiral phase plate, automatically it becomes a helical beam. Next, another way we can generate using uniform circular antenna arrays, which is shown in here. We will place these antennas at different certain regular interval in terms of, you can say, theta. Okay, then automatically it will generate a wave. Another ways we can also use this to generate this wave. Already we have in our our group already generated. Professor Jugesh Chaukikar will tell you during his discussion or lecture how this can generate this wave. Now, if we look at this is basically I took a simple block diagram for OAM using OAM signal generation. Means basically I would better I say the data how OAM mode can be used to transmit a data, okay, or data stream. Now, say there are multiple users are there. So for multiple users, multiple modes I have to use. So in that case, how the transmitter looks like or the transmitter system looks like. So user data 1, that basically it is showing the multiplexing, how it is multiplied. User data 1, user data 2, up to n number of user data is there. They are modulated, then pass through wave generator. Say it is 1, it is 2, it is 3. It may be some -3 randomly it is given. Okay, then after modulation, after that data incorporated in given mode, then they pass through a beam splitter. Okay, pass through beam. This beam splitter, better I say beam combiner, they will combine the different wave signals and make a composite or multiplexed wave beam, which looks like this. So that's what these symbols are then fed through a wave generator, which maps the modulated signal onto a particular wave mode. These wave generators provide orthogonality between users in a spatial domain by providing unique helical phase form beams, and 3dB beam splitter are used to combine the selected signals from a various wave generator superimposed several wave modes to generate a single multiplex. That this multiplex beam is transmitted. It is used for multi-user transmission. Similarly, when I think about see the OAM receiver, it has a receiver plate. This is the receiver plate. Each and every receiver has this OAM receiver. Okay, what happens that this multiplex beam, which one is transmitted? This multiplex beam is received here, received here. So the multiplex beam initially hits the receiving plate at the receiver, capturing the incoming spatial field. The receive already that each receiver is it is not like that say there are two each any receiver can decode any type of any mode. No, there are particular modes are there. So user codes mode 1, user 2 mode, you can decode mode 2. So accordingly these receiving plates are used or designed. So the received field gets analyzed to determine the wave mode of the intended users. Then what it does, then the receiver then isolates the desired wave component, because there are multiple wave components are there, multiple modes are there. It will just select the desired mode and allow the desired mode to pass. Okay, thereafter uh, perform the mode projection by correlating the received field with the basis function L e to the j power, or then it performs the mode projection. Then automatically once it performs the mode projection, then it can extract its desired beam, desired mode, and once the mode is it is detected, that desired mode is detected, then it will decode the its in the signal. This is how the receiver works. Now, so now, if we look at back, we now come to know what is why WAM is required, what is WAM, and why WAM, how WAM works. All this already I've discussed. How it looks like, what is its intensity, what is its phase structure. That all, everything I discussed. Now I move to that LG beam. LG beam basically, you can say it carries the wave. How I can LGB is Ligar Gaussian. How I can describe this LGB? So this is the expression of LGB, where this part is basically, this part controls that. I already told you that that beam is propagating. Say this is the direction that beam is. See, this is the beam. This is the beam. It is propagating along the Z direction. Say this is the Z direction. Z direction. So it looks like this way. It is like when it propagates, it diverges. It diverges. So one is that Z direction, another is this radial direction. The intensity is varying both directions. Z direction, along the direction it is propagating, as well as the radial direction towards it is diverging. So this portion, the first part of that is encircled here, that already enclosed by the red line. It is basically defines the change in intensity along the Z as well as along the radius under this person. This basically tells about your phase structure, and this how it is decaying along the Z direction when it is propagating. This described by this e to the power j minus jkz. In this equation, L is the basically azimuthal, that is a mode index. P is the radial index number. I'll tell you P. That is the P shown here. P is the radial index number. R Z. Sorry. There is a R phi Z. Basically, this is that is a cylindrical coordinate for cylindrical coordinate systems. WZ is basically beam waist, where see WZ can be described as W0 to the root over 1 plus z by zr whole square, where W0 is basically the beam waste at z is equal to 0. At 0, this is the initial point, z is equal to 0, beam waste. So when it propagates along, when it reaches to z, there is a Rayleigh distance. Here the beam waste becomes twice of the under root of one is square root 2 of this W0, and this is called Rayleigh distance. This is called Rayleigh distance. And if you look at this figure, it shows the distribution of this intensity. At center, it is the intensity is 0. So if you look at, when you look at here, if you look at the figure that beams at center, if you look at here, see here, that one is describing the yellow line, yellow, and that black is 0. So at center, the intensity is 0. At center, the intensity is 0. Okay, and this yellow line is basically having the highest intensity. So similarly, you can see the intensity if you look at here, that how the intensity is varying radially. So from here it is 0, then it's like a Gaussian distribution. Gaussian distribution. So that's what the next you can see that the same thing here is mentioned. That is this the Ligar polymer describes the radial intensity distribution of the beam, and it determines the shape of the concentric rings. Means concentric rings means basically these are the concentric rings. This one, these are the concentric rings. Gaussian envelope, how the that Gaussian envelope decays, then helical phase structure, that is e to the j phi L. Helical phase produces spiral phase structure that I already told. And another is the already that is mentioned propagation phase term, that is the e to the j phi kj along the z direction. The beam is this is the direction basically of propagation, and this is your enter beam. Okay, so e to the j phi minus j k z is describing the propagation phase. K is the wave number here, 2 pi by lambda. Lambda is the wavelength of the transmitted signal. Now, if we look at here, that already I mentioned, this Ligar polynomial basically tells about the intensity distribution along the propagation direction Z as well as the radial direction R, where P is the radial index. P is the radial. It can tell you how from this P you will come to know how many rings are there. Total number of rings is basically P plus 1. It is if P is equal to 0, that means there will be 1 ring. If P is equal to 1, that means there is a 2 ring. If P is equal to 2, that means there are 3 rings. Just look at the next example. Say L is equal to 0, P is equal to 0. So it's a bright spot. When L is equal to 0, P is equal to 1, that means P, since P is equal to 1, so there would be 2 rings. So this is 1 ring, this is second ring. If P is equal to 2, there would be 3 rings. 1, 2, 3. So every cases you can find 3 rings. 1, 2, 3. Here also 1, 2, 3. But if you look at, if I increase the value of L, the width of that rings, each ring increases. The width of the each ring increases as the value of L increase. That means the modes basically affects the radial distribution. Okay, and P basically gives you how many concentric rings are there. Now, I'll take first system model 1, where you can see that there is a transmitter, and there is one receiver, another is a 2 receiver system. Okay. So the transmitter is basically simultaneously transmit informations to user receiver 1 and receiver 2 using OAM transmission or OAM multiplexing. For user 1, that is for RX1, it uses L1 mode. And for user 2, it is using L2. So if the user data is X1 for receiver 1, user data is x2 for receiver 2. So what would be the composite signal? That is st is equal to, I can write under root of p1 x1. That is basically, I already mentioned that information would be transmitted using LG beam. LG beam is basically representing the wavelength. So X1 is basically user information and P1 is the transmit power. So since it is taking, for the first part is taking care, means carrying the user one information. So that's what, and it is using mode L1. So UL1, that LGB is denoted with UL1. Whereas in the second, if you do the second part of this ST, this information of information X2 for user 2 and LGB, that is with mode L2. These two are combined and that ATX is transmits this ST for both. Since these modes L1 and L2 modes are orthogonal to each other, they won't interfere each other. They are transmitted to the same band. That RX1 basically decodes that first part, and that is a L1 mode information, and RX2 will decode the second part, that is a L2 mode. Already I mentioned in this slides, if you look at the previous slide, that each receiver has that OAM receiver in such that receiving plate is designed in such a way for each receiver, it can receive a particular mode. So obviously, for user one, it will allow only L1 mode, and for user 2, it will allow only L2 mode. So anyway, the transmitted composite signal ST can be described by this equation. After transmission, this ST will reach to RX1 as well as RX2 through this link or channel. These channels are not normal convention channels. Keep in mind, these are OAM channels. Normally, if you look at the conventional communication system, what we used to do, for the same case, we used to write, say, ST is equal to, for conventional system, we used to write root P1, X1 is transmitted plus under root of P2, X2 information. This information is transmitted over the channel, that is H. So the receiver that is, say, YRX1, if I write, so it would be, say, if I say it is a H1, say for a conventional channel, we used to write H1 into ST plus N. And for YRX2, we used to write H2. So if it is a H2, ST plus N. This H1 or H2, they normally we used to consider for normal RF communication, we used to consider they are Rayleigh faded or Raysian faded if there is line of sight. So then Raysian faded if there are no line of sight. Rayleigh faded, we can consider Nakagami. Okay, so different statistical channel models are there we can use for the performance analysis. But over here, since we are transmitting wave signal, the channels are wave channel. That's what the description is little bit different from the that is a conventional one. There is a basically this GT transmitter receiver gain, because I have to that link I have to consider. Lambda is basically the wavelength of the signal. This DI is basically DMN in this figure. You look at carefully. This is the, say, transmitter. That if it is use a circular patch antenna, circular that previously that if you see here, this antenna. This antenna is used. This antenna is used to generate that. See. This is one antenna, this is another antenna, this is another antenna, this is another, this is another, this is another. So there are several antennas placed at regular or certain means on a concentric circle, on a circle at a different at a equal distance or better equal. Their separation is same. If we look at the same type of circular, if I use antenna array, if I use, it looks like this. So this is basically transmitter, and similarly same type of receiver I have to use at the receiver. Now, what is this DI? DI is basically this line, this line. This line means, see, beam, when the beam propagates, it will diverge. So if that's what it is, a small circle, it is a big circle. Beam will diverge. So this antenna, if I think about this emith antenna, is receiving signal transmitted from this emith antenna is received by this nth antenna. So the distance between these two is basically this DI, this DI. Okay. Then how I can find this distance? So I have to take a projection, because this is a bottom ring, this is the upper circular ring. I have to take a projection. This is basically perpendicular. This is, you can say, base. So if I say this is A, B, and this is C, it looks like this. Looks like this. This is B, this is C, this is one is transmitter side, TX side, and this is RX side, and this is A. So this is, so what is this value? So CA is equal to, I can write under root of BC square plus AB square. This is how I can find out this distance D. So this D is used here, and this is basically that how the angle is varying with the distance, this one, and this is basically, this is uh, due to the mode or phase variations, this e to the power j l phi I within the channel. So this HRIL indicates the OAM channel. Here, since I am transmitting two two modes, for each mode, there would be one link. For each mode, normal communication, if we think about a normal communication, transmitter to receiver, we used to consider, if they are using the single antenna system, we used to consider a single link, that's H. But here it is little bit different. Since the transmitter is transmitting two modes, each mode to receiver will be treated as one link. So the channel structure become this one. Channel structure become this one. For this is for user 1, for L1 mode channel, for L2 mode channel. Similarly for user 2, L1 mode channel, for L2 mode channel. Clear? And each one can be described by this one. Each one should be described by this wave channel. I think it is now it is clear how to model the channel. Now, so what would be the received signal? How we can describe? So if you look at here, the received signal, this is basically describing the channel. This is the transmitted symbol, and this is that FR, which is related function of R. I'll tell you in I. Normally, if we look at here, that transmitted signal is ST, where LG beam is there. And if you look at the LG beam, there is an impact of R as well as the impact of Z. Both are there. So when I'm describing the equation, that transmitted signal, I'm using this LG beam when, and as well as where the impact of A, R, and Z all are there, and this is the channel. Then when I'm describing the received signal, so see here, this part is basically is a function of that R and D. Okay, here this is basically describing that function of sorry, I think Z is missed here. It should be Z is also there. Okay, and this is the basically signal part that was transmitted, and this is the AWZ. So basically, this is the user 1, user 2 information, and rest part is basically coming for wave transmission. Rest part. Okay. So what since now I now see just go back. Already I mentioned that receiver one is receiving signal for L1 mode signal, L1 mode signal, L1 mode signal plus L2 mode signal. But its receiver is designed in such a way it will, if you look at here, I already mentioned, it will this receiving plate will allow only L1. So it will discard L2. So only it can process L1, it will discard L2. So there is no chance of interference here. Similarly, it will allow only A to L2, it will not allow discard L1. So that's what you can see here, that SNR is equal to Pi mod of HIL square by sigma n square. If we think about a normal communication that I wrote already here, this one, just I'm writing once again. Say if I think about RX1 point of view, means receiver 1. So receiver 1, RX1, YRX. So it is basically H1 into that S plus noise. What is S? H1 into under root of P1 X1 plus under root of P2 X2 plus noise. So basically, this is my received signal under root of P H1 X1 plus under root of P2 X2 H1 plus noise. For receiver 1, the signal part is this one. This is basically interference because it is the signal of user 2 and this is noise. So in that case, I will get SINR, which is equal to P into mod of H1 square and H1 square by P2 into mod of H1 square plus sigma n square noise variance. So if you compare this one and this one, this is the conventional system. So you can find SI, SNR I is much greater than SINR for conventional system. So that's what, since SNR is high for wave transmission, obviously the link capacity for each user would be high and the sum rate would be high. So which is one result is given conventional transmission system and wave transmission. If you look at here, so with the increasing SNR, both are increasing, conventional and that wave transmission link capacity sum rate is increasing. Sum rate means basically data rate of user 1 or throughput of user 1 plus throughput of user 2. That is called sum rate. So if you look at here, that wave transmission, that sum rate for wave transmission is outperforming the conventional transmission. For a given SNR, for say 20 dB SNR, here approximately 2 bits per second per hertz. That is where in conventional system, whereas in OAM system it is more than approximately 10.1 or 2 bits per second per hertz. So obviously that OAM transmission is much more advantageous over conventional system. Next part, uh, mode coupling and crosstalk. See, previously I wrote one channel matrix, that one user 1 and user 2. See here, that just a minute. That channel matrix H is equal to, I wrote H1 user 1 L1 mode 1 H1 L2 H user 2 L1 H2 L2. Ideal condition, in ideal conditions, elements these elements are zero. In ideal conditions, these elements are zero. Okay. In ideal condition, this matrix becomes basically H1, comma L1, H1, so that becomes zero. This becomes zero. It is H2, L2. But if they are not zero, that means what physically it indicates? It indicates that L2 mode transmission converted to L1 mode, and the user 1 accepted the or decoded the signal. Similarly, in this case, L1 mode converted to L2 mode, and user 2 decodes the signal. That means in this case, the L2, H1, L2, that user 2 information will need create interference to user 1. Similarly, for this, in this case, user 1 signal will create interference to the user 2. So this is called mode coupling, and due to this, crosstalk occurs. So mode coupling or OAM crosstalk occurs when the transmitted OAM mode does not remain perfectly orthogonal during propagation or reception, causing energy from one mode LT2 leak to another mode LR. What I told you. See, mode L is equal to 0 is transmitted, but during transmission or propagation, this 0 converted to L is equal to 1. So it is a mode leakage. So if it is happening, then there will be a mode coupling or crosstalk. So which physical phenomena are responsible for this mode coupling? One is atmospheric turbulence. Transmitter receiver misalignment means if the antennas are not aligned properly, transmitter and receiver, then this mode coupling occurs. Receiver aperture is finite. Receiver aperture is finite. Say if you place your receiver little bit far away, and if not far away, say some at a distant distance, but since the nature of the beam is, when it is propagating, it is diverging. So entire entire, because already told you, when it is propagating, it is diverging. That means that entire mode may not come into this aperture of the receiver antenna. In that case, that mode coupling may happen. Beam divergence, if it is diverge, already told you that is it mode spread faster, higher mode. If you set the higher order modes, it diverges faster. In that case, mode coupling occurs and multipath cascade. So these are the reasons why that mode coupling or crosstalk occurs. Now I'll talk about this is my last slide. Where I'll bring, since I want to relate this discussion with the last discussion with the risk, where already seen before going to the discussing the results, I have to draw the network structure. See the same structure I'm taking. See, this is a transmitter. This is I'm placing the reese here. I'm placing the reese here. And there are two, receiver 1 and there is receiver 2. So normally it hits, then my drawing is not good. This one. See, here the interesting, this our work already under that is reviewed. So I cannot disclose that entire work, but okay, I'll give you that idea about this. When I use the these, what would be the channels basically? This is the channels are interesting here. See, the dimension of this is n, and it is, since there are two users, it is using say L1 and L2 modes. Each mode, each mode already mentioned, each mode to the each element, these are the elements, one, two, three, four, these are the these elements. Each mode to each element becomes one channel. So if I think this would be one element, can I change that? No, I cannot change that. Is there any possibility of changing that color? Okay, anyway, if I think about say this element, k, say I'm considering this is kth element. So from the kth element to tx, in normal communication, in conventional communication, there is one link. But since this transmitter is transmitting two modes simultaneously, there will be two links for each element. If the transmitter transmitting three links for each element, there will be channels three channels. Say if the modes are L1, L2, L3, for L1 there will be one channel from TX to this kth element. For L2 there will be another channel, or for L3 there will be another. For each element there will be one channel, one-to-one mapping. For each element, the number of channels from transmitter to the receiver will be number of modes. How many modes it is they are using. So I can say, since there are n number of elements and there are two modes, I can say that transmitted to TRS, its dimension becomes n cross 2. N cross 2. Now, how I can explain this HTRS? How I can describe HTRS? TRS is equal to, I can write H T R S, say HTRS 1. This is HTRS. This is basically element number. It is describing. It is describing the element number. Similarly, element number 2, say I'm taking, this is one element, this is two element, this is three element, like dot 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 blah blah. This is k and this is nth element. This is kth element. This is nth element. So HTRS 2 dot dot HTRS n. And what would be this HTRS k? That HTRS k, k value can be 1 and 2, k can be 1 and 2. It would be H for say I should say kth element, and transmitter 2 for L1, say L1, say I'm writing similarly, just for a notation for L2. So for similarly for each one I'll get 2, 2, 2, 2, it becomes n plus 2. Similarly, when I'm thinking from reach to that ith user, so it would become another set of channels. So end-to-end channels. Now I'm describing, say this is HTR and this is, say this is for ith user, HRRS I. I is equal to, if I use I is equal to 1, then user 1. If I use I is equal to 2, then user 2. So end-to-end channel, HE2E, end-to-end channel, I can write HTRS, then that phi is basically indicating the risk parameter, where that reflection angle as well as the uh, phases of each element is considered into H R R S I. This will be the channel, end-to-end channel. If there is direct, no direct links are already blocked. Then I can discuss what is the ith signal. Hi is equal to, I can write and see these HL2 all are these OAM channels. These channels. This one, OAM channels. All are described. So very interesting. So when you go in depth, you'll find there is a uh, lot of things are there to discover. Okay, it's interesting this channel modeling. Anyway, what would be the received signal? Yi is equal to, I can say now, since it is transmitted S, so I can say it is E into S plus noise. So if I model this SNR, sorry, SNR, I can model SNR. I can model link capacity using this equation. Link capacity. I can model sum rate and all. So here one result is given for sum rate without risk. That previous system, what I considered, the previous system where there is no risk, this one. And now if I consider any that with the risk system, just I place the risk, how the system performance improved, that you can see in this result. Just I use the 4 elements. Normally, this would this H E to E is always proportional to n square. That already I discussed. I cannot remember whether I told or not. That gain, this is basically proportional to n square. So anyway, you can see that red line, that is basically without risk, and blue line with risk. You can see for given SNR that when I place the risk, it is getting higher or better sum rate. So that's all for today. Now I'll conclude. Future that OAM communication is considered as a promising candidate technology for next generation wireless networks such as 6G. It can potentially provide extremely high data that I already mentioned, support massive connectivity because there is a that all the modes are orthogonal to each other. They can't interfere to each other. So we can use um, more number of modes to accommodate more number of users. So and you may make it the spectrum more efficient. Integration of web with other emerging technologies such as massive MIMO, decommunication, REIS that I already discussed, free source optical communications may achieve significantly higher capacity and more flexible wireless environments for future communication. That's all for today. Uh, okay, fine. Any question? Any question? Bhaskar, could you hear me? Any question?
Yes, sir, you are audible, sir.
Okay. If you have any questions, you can place your question in the chat box. We'll reply. Thank you. Thank you all for joining. Hope it will help you.